Welcome back. In this video, we're going to start chapter 8, which is about rational expressions and equations. As always, when we start a chapter, it's a good idea to look ahead and see what it is that we're getting into and go from there. So this chapter is really kind of long, but we'll make our way through it. Basically, the quick idea of the whole chapter is that it's about fractions, and the fractions have as numerator and denominator polynomials. So we've seen before how to work with polynomials, how to factor them, add, subtract, multiply, and divide polynomials. This chapter is about having fractions where the top and bottom are not just numbers, but are instead polynomials. So how to go through this, or let's go through this and see what each section is about. 8.1 is about simplifying rational expressions. So this is a part where essentially we're looking at simplifying or reducing fractions. If you remember from arithmetic how to change 4/8 into 1/2, then you're already halfway there, just about. That's the idea. How do you simplify a fraction where the numerator and denominator are polynomials? 8.2 is about multiplying and dividing fractions, rational expressions. And then 8.3 and 8.4 are both about adding and subtracting rational expressions. It's divided into two sections because usually people find adding and subtracting a little trickier than multiplying and dividing due to the whole common denominator thing. To add and subtract fractions, you need to have common denominators. And so the first section, 8.3, is how do you do it if there's kind of already a common denominator? And then the next section, 8.4, is if they're unlike denominators, and we'll see that kind of the pre-step that you have to take is make it so that the denominators are alike. Okay, once we've done that, we'll go on to section 8.5, which is about complex rational expressions. What a complex rational expression is basically a fraction with a fraction inside of its numerator or denominator or both, as we'll see. And the main thing we do in that section is simplify these expressions. Section 8.6 is about solving rational equations. So just like we saw with polynomials, you can do a lot of work with polynomials where the answers are polynomials. And then when you go to solving equations, the answers are numbers that make the equation true. We'll see a similar jump here after you've seen how to add, subtract, multiply, and divide rational expressions. When we make the jump to equations, we'll end up with numbers for answers. The last three sections in the chapter are all story problems, all applications. Section 8.7 is about proportions and similar figure type situations. Section 8.8, uniform motion and work problems. We've dealt with uniform motion before, where we have two objects, planes, boats, trains, people, or whatever, heading toward or away from each other, and we answer questions about it. And then 8.9 is about specific kinds of word problems involving direct and inverse variation. All right, so that's the whole thing, like I said, fairly lengthy. The heart of the chapter really is in the first 6 sections. So let's go ahead and get started on section 8.1, which is about simplifying rational expressions. So really the first thing to do is make sure we know what a rational expression looks like. I had mentioned that they're fractions where the numerator and denominator is a polynomial, and that's true. A rational expression looks like P over Q, where P and Q are polynomials, and Q is not allowed to be 0. As you recall, division by 0 is undefined, so that was not an issue with polynomials because there was no division. But now that we're working on fractions, we have to make sure we're not dividing by 0. Some examples of what rational expressions look like: 2 over x, x plus 7 over 3x plus 5, as well as the others. I did want to pay attention to the fact that 5 is also a rational expression because you can't always write it as 5 over 1. So any number, or in fact any polynomial, can be considered a rational expression that has a denominator of 1, if you like. Okay, one of the first tasks that we'll want to be able to perform is to know when a rational expression is undefined or not. And as I'd mentioned, division by 0 is undefined, so we have to look and see what values of the variable would make the denominator 0. So for this first one, we have 3y over x. This will be undefined if x is equal to 0. It's okay if y is equal to 0. It's all right for a fraction's numerator to be 0, just not the denominator. Okay, for the next one, we have 8n minus 5 over 3n plus 1. Again, the denominator is what we have to worry about. The numerator, it doesn't matter what the numerator is. We do need to find out what those make the denominator 0. So we'll solve the equation 3n plus 1 equals 0. And so it'll turn out that n is negative 1/3. So that would be a value we would need to exclude from the denominator. For the last one, our denominator is a squared plus 4a plus 3. Once again, we'll set that equal to 0 to find out the values of x that will cause our expression to be undefined. And so for that one, we get to practice our factoring, which maybe has been a little while since we've done that. We're looking for two numbers that multiply to be 3 and add up to be 4, and that should be 1 and 3. And so using the zero product property, either a plus 1 is 0 or a plus 3 is 0. So that means that either a is negative 1 or negative 3. Those would be the two values that we would need to exclude as they make the expression undefined. Okay, the next task that we'll want to be able to do is evaluate an expression. Evaluating expressions, what that is about, you can get that from the second through fifth letter, the ALU. It means that we're getting the value of an expression. So typically we're going to replace the values of variables with some numbers and then calculate a numerical answer. So here we've got y plus 1 over 2y minus 3. We're going to evaluate it for y equals 1, y equals negative 3, and y equals 0. All right, so let's try that first of all for 1. I'm going to replace the y by a 1 everywhere it occurs, and then compute an answer. So we have 1 plus 1 or 2 in the top. 2 times 1 is 2. 2 minus 3 is negative 1 in the bottom. That will be negative 2. Okay, let's try it for negative 3 next. We'll have negative plus 1 divided by 2 times negative 3 minus 3. That will be negative 2 in the numerator, and then negative 9 in the denominator. That will give us 2/9. 0 next. If you were concerned, well, I thought the denominator could be 0. That's true. The denominator is not going to be 0. We don't have just the variable in the denominator. We have 2y minus 3. So it turns out our denominator here is going to be negative 3, giving us negative 1/3 as our final answer. Evaluating expressions. Okay, here's one for you to try. Take a minute, pause the video, and then try this yourself, and then restart it and make sure that you get the same answers as I do. If you don't, rework it till you do, or let me know if you have any questions. All right, so we're evaluating this thing first of all for 0. I like working with zeros because often it's easy to multiply by 0 or add 0 is easy to do. So we should end up with 1/2 for the first one. Next, we're going to evaluate it at negative 1. Okay, so negative 1 squared is 1. 1 plus 1 is 2 in the numerator. Negative 1 squared is 1. 1 plus 3 is 4. Plus 2 more is 6 in the denominator. Don't forget to simplify your fractions. We're going to end up with 1/3, it looks like. And then lastly, we're going to put a 3 in there. So we will have 3 squared plus 1. 3 squared minus 3 times 3 plus 2. 3 squared is 9, plus 1 is 10 in the top. 3 squared is 9, 9 minus 9, it's a little careful, and then plus 2 in the bottom, 10 divided by 2, 5 for the last one. Okay, only one more of these evaluate examples. For this one, what's different is we have two variables in our expression. So we have 2a cubed, here our a is negative 1, and then a b, which is 2. Make sure that you put the right value in the right place. It was the a that was negative 1, it was the b that's 2, so be careful you don't get those switched. A squared plus 2ab plus b squared If you don't mind, I have no way of, sorry. I'm going to go ahead and factor that. That way I only have to put down the value once. We'll make that a plus b squared. So this will be -1 plus 2 squared. To me, that's easier than evaluating the polynomial we were given in the first place. Okay, -1 cubed is -1 times 2 is -2. We'll do this in a couple of steps. Down below, -1 plus 2 is 1. That's nice. 1 squared is 1. So I think we get -4 for that. All right, and that takes care of our evaluating step. The next thing we want to be able to do is to be able to simplify expressions. That's kind of like reducing a fraction, if you like. So for a fraction or rational expression to be simplified, we can't have any common factors in the numerator and denominator other than 1, of course, which will always be there. How you get that done is by using the fundamental property of fractions, which goes by a variety of names, but this is what I call it. And what it says is if you have, here it is all in symbols, but what it says is if you have a fraction, you can multiply the numerator and denominator of that fraction by a number c, without changing its value. If you read instead right to left, you can divide the top and bottom of a fraction by the same non-zero number and get a fraction with the same value. So we use that to help us simplify fractions. We're going to try it right here on this -45/81. 45 is 9 times 5. 81 is 9 times 9. We can divide the numerator and denominator by 9. And then that will simplify our fraction. We'll have -1 times 5 is -5. And then 9 times 1 is 9. So we just get -5/9. We divided the numerator and denominator of our fraction by 9. We do the same basic thing, or the same exact thing, when we are working with variable expressions. So it may help you, especially if you're just starting out, to like literally write out all the factors. We'll do that this one anyways. We have 4x squared y, so that's 4 times x times a y. Down below, I have 12xy squared. I'll leave the 12 as is. If you want to factor the numbers, make that 4, 2 times 2, and the 12, 2 times 2 times 3, you can. I don't have a lot of patience for that. Okay, so we have 4 on top, 12 on the bottom. Down below, we have x times y times y. All right, so then we want to see about dividing out any common factors. The numerator and denominator both have a y in there. So we're going to divide the top and bottom by y. That leaves 1. We're going to divide the top and bottom by an x. Kind of hard to cross out an x. Okay, and that will leave behind 1s. And then 4 and 12 are both divisible by 4. 12 divided by 4 leaves a 3. Okay, multiplying across what's left, 1 times x times 1 will give us an x in the numerator. Down below, we'll have 3 times 1 times y times 1, and that will be 3y. Okay, so we divided out all of the common factors. Okay, let's try that again with one that is a tiny bit more complicated. 3x minus 6 divided by 2x minus 4. I'm going to start by factoring out that common factor of 3 in the numerator, and in the denominator, we'll factor out the common factor of 2, and that will leave 2 times x minus 2. On this one, the x minus 2's are common factors, so we will divide out both of those, and that will leave just the 3/2. Okay. It's important to note that when you're applying that fundamental property of fractions, you need to have the numerator and denominator factored. If I were to try something like this, like say, okay, well, 6 and 4 are both divisible by 2, so let me do that. That's wrong. You can't do that because the numerator and denominator aren't factored. We haven't divided the entire numerator and denominator by 2, just one little term out of it. Okay, and so that's wrong. Be careful you don't do that. We need to have the numerator and denominator factored before applying that fundamental property of fractions. Okay, let's move on, some more examples. Okay, so here we have a quotient of a couple of quadratic polynomials. So let's go ahead and um, simplify this. So here we're going to need to factor the numerator and denominator. So here you're going to get a lot of practice with your factoring, okay, for better or worse. So in the numerator, we need two numbers that multiply to -2 and add up to -1. Sounds like x plus 2, x minus 1. Let me double check by multiplying that back out. If I did, I would x squared, I'd have minus x plus 2x minus 2. So I've actually got the signs here backwards, so let me fix that. Okay, let's try that again. That's x squared plus 1x minus 2x. That's better, and then minus 2. Okay, remember you can always double check your factoring by multiplying back out. Okay, so now the bottom, we need two numbers that are the same sign and both negative. We need them to multiply to 2 and add up to 3. So that would be 2 and 1. So now that we've completed our factoring, we can see that the numerator and denominator are both divisible by that x minus 2. So let's go ahead and divide that out. That will leave us with x plus 1 over x minus 1. Once again, don't get cancel happy and cross out the x's here. Okay, the numerator and denominator don't have any more common factors. You can't cross out the x's, cross out the ones, or anything else. We are done with it here. Okay, down below, here's one for you to try. Take a minute, pause the video, try this one yourself, then restart the video and see how you did. Okay, so once again, we're going to need to factor both the numerator and denominator. I'll start with the numerator. We need two numbers that multiply to -6 and add to +1. So I'm going to say x plus 3, x minus 2. Double check by multiplying. We'd have x squared minus 2x plus 3x minus 6. That looks good. Down below, we have a difference of squares. That'll be x plus 2, x minus 2. Here, once again, the x minus 2's will cancel out. That leaves us with x plus 3, x plus 2. Okay. All right, this one looks a little bigger, but I think we can do it. Down below, there are 4 terms. There are no common factors. When there are 4 terms, as you recall, we're going to try factoring by grouping. So let me factor that by grouping. The first 2 terms have y squared as a factor. The second 2 terms are just y minus 3, so our common factor is 1 there. So this will be y minus 3, y squared plus 1. Down below, we'll have y minus 3, y plus 2. In simplifying these fractions, these rational expressions, you'll find that a lot of the work is doing the factoring, actually. Okay, so we've got y minus 3, y squared plus 1 in the top. Down below, we have y minus 3, y plus 2. Here, the y minus 3's will cancel out using the fundamental property of fractions. And so what's left is just the y squared plus 1 divided by y plus 2. As you recall, the sum of squares, that y squared plus 1 is not going to factor. So that's the end of that. Okay, here's one more for you to try. Take a minute, pause the video, try this yourself, restart the video, and see how you did. All right, so working on the top first, it looks like a common factor of 2n can be removed. So if I bring out 2n, we'll have n minus 5. So that's what our top looks like. Down below, there's a common factor of 4, at least. Yeah, just 4. And so if I factor that out, we'll have n squared minus 4n minus 5. And so the degree 2 polynomial there, not a perfect square. We need 2 numbers that multiply to -5 and add to +4. Sorry, add to -4. So n minus 5, n plus 1 looks like it'll do. Let me double check by multiplying. We'll have n squared plus 1n minus 5n's minus 5. So that looks good. Okay, so putting together the pieces that we factored, we'll have 2n, n minus 5 in the top. Down below, we'll have 4. minus 5, n plus 1. Okay, make sure that you understand the factoring before you go any further. So now the two factors of n minus 5 can be divided out. So if we do that, what's left is going to be 2n in the numerator, and then 4n plus 1 in the denominator. But wait, there's more, right? The 2 and the 4 can be divided out, actually. So with, hold on, let me finish this. N over n plus 1, 2n plus 1. If you multiply to remove the parentheses, you'll have n over 2n plus 2. All right, so what I was about to say was that simplifying fractions is kind of like factoring. When you do it, you want to go all the way with it, right? Where I'd almost stopped right here, there was still a common factor of 2 that could be removed. You want to simplify as much as you possibly can, take out any possible common factors that there are. All right, that takes us to the end of the first part of section 8.1. In the next video, we'll see basically just more examples of simplification. In the meantime, let me know if you have any questions, and have a great day.